All right, so here in example number 7, we have a process where monochlorobenzene is produced commercially by the direct catalytic chlorination of benzene. So benzene plus chlorine gets monochlorobenzene. And then in the process, dichlorobenzene is generated as a co-product. Liquid and gas streams leave the reactor. We know the liquid composition by mass percent, and then we know the gas composition by volume. And we are to assume ideal gas behavior for the gas stream. And we want to figure out what volume of gas leaves the reactor in cubic meters per kilogram of benzene fed. So first, we need to figure out the liquid composition in in terms of like molar composition. So we are going to assume a basis of 100 kilograms of liquid. So then, if we have 100 kilograms of liquid, we have 49.2 kilograms monochlorobenzene times or divided by its molecular weight of 112.6 kilograms per kilomole. And that gives us 0.437 kilomoles of M. And then we're going to do the same for D and B. So 29.6 kilograms of D times 1 kilomole has 147 kilograms. So that gives us 0.201 kilomoles of D. And then for B, we have 21.2 kilograms of B times 1 kilomole has 78.12 kilograms. So 0.271 kilomoles of B. So then total, we have 0.437 plus 0.201 plus 0.271. Total, we have 0.909 kilomoles. So then the composition on a molar basis is 0.437 over 0.909. So it's 0.481 monochlorobenzene .221 dichlorobenzene and 0.298 benzene. Okay, so now let's draw out our flow chart. And this basis was just for us to get a the mole fractions of each of these components in the liquid outlet stream. We are no longer gonna go ahead with that. Our new basis is going to be 1 kilogram, 1 kilomole of C6H6, and then some number of moles of Cl2 also enter the process. And then we have our gas stream leaving and our liquid stream leaving. So our liquid stream is some volume at 40 degrees Celsius and 120 kPa. And that also has some molar flow rate. And the composition is 0.92 HCl and 0.08 Cl2, and that was given up here. And then we have our liquid stream leaving, which has some total number of moles. It's not this total number of moles. We just use this in order to figure out the composition, because the composition is not dependent on like the actual flow rate. So we just assumed this basis to get these mole fractions. So some number of moles of liquid flowing here with a molar composition of 0.298 C6H6, 0.481 C6H5Cl, and then 0.221 C6H4Cl2. So then what we're going to do is, so we have our equations up here. We are going to start with a carbon balance. And so going into the process, we have 1 kilomole C6H6, and that has 6 carbon, sorry. And then coming out of the process, we have no carbon in our gas stream. We have N2 times 0.298 times 6 plus 0.481 times 6 plus 0.221 times 6. And so that ends up giving us that okay. So that ends up giving us that N2 is equal to 1 kilomole. So we have 1 kilomole of liquid leaving the process here. Now we're going to do a hydrogen balance. So for hydrogen, we have 1 kilomole C6H6 times 6 moles of hydrogen in benzene. And then that is going to equal that is going to equal, okay, yeah, 0.92 times 1, since there's 1 mole of hydrogen here in HCl, plus N2, which is just 1. Oh, sorry. I forgot to include N1 here. So it's going to equal N1 times 0.92 times 1 plus N2, which we know is just 1, times 0.298 times 6 plus 0.481 times 5 plus 0.221 times 4. And that ends up giving us that N1 is also equal to 1. So N1 is 1 kilomole as well. Now, we are going to use the ideal gas law. So that is PV equals nRT, and we're going to rearrange that to solve for volume. So that's going to equal to V1, which is our volume of gas leaving the reactor. V1 is going to be equal to N1 RT over P. So N1 is equal to 1 kilomole times R, which is 0.08206 meters cubed times ATM over mole Kelvin, and then times the temperature, which is 40 plus 273, so that's 313.15 Kelvin over 120 kPa. And then we're going to multiply this by, there's 100, not 10, since we need this in terms of atmosphere. There's 101.3 kPa per atmosphere, and then everything else is in the correct units. Except here, I should have written this in kilomole. Okay, so that ends up giving us .7 cubic meters. But they want us to answer this in terms of cubic meters gas leaving per kilogram of benzene fed. So that is actually going to be V1 over the benzene fed, which is going to be 21.7 cubic meters over, we have 1 kilomole of benzene being fed, and the molar mass of benzene is 78.12. So 78.12 kilograms, since there's 1 kilomole being fed. And that is going to equal .278 cubic meters per kilogram of B fed.